The second practical application of acid-base equilibria that we'll look at is that of buffers. So first of all, we're going to define what a buffer is. So a buffer can be defined as a solution that resists change in pH upon addition of small amounts of acid or base. So what do we mean by resists change? And generally it's defined as being, better than water. So it should be more resistant to changes in pH than pure water. And real-world examples of buffers would be things like human blood, which has a buffer which buffers at around about 7.4 pH units. There are other biological systems as well that do this. The ocean tends to buffer around about 8.1, and then we have freshwater systems like lakes and rivers. Most of the rivers, they tend to buffer around about 7.4. Things like rain are also buffered. Rain is consistently has pH of around about 5 to 5.5. So buffers are a naturally occurring phenomena, but we also use them in the lab. So typically what a buffer will be is a solution containing a weak acid in equilibrium with its conjugate base. So keeping in mind that a conjugate acid-base pair are just two things that are different by one proton. So classic examples of weak acid conjugate base pair buffers would be something like acetic acid acetate ion buffer or carbonic acid bicarbonate ion buffer. So your acid does need to be a weak acid. So we can't do this with strong acids. So how do we get a sort of like significant concentration of the conjugate base? Remembering these are weak acids, they don't like to make a lot of that. What we generally do is we'll add an ionic compound that contains the conjugate base of our weak acid. So if we want a buffer that's built up of acetic acid and the acetate anion, typically we will add a source of acetate anion using something like sodium acetate. We like to use sodium acetate over other forms of acetate anion because the sodium ion is derived from the strong base sodium hydroxide, and it's neutral, it won't affect the pH. So sodium salts are popular for that reason. Sodium salts are also popular because they have good solubility. So if I was building a buffer that was based around the carbonic acid bicarbonate anion system, and then I would want a source of bicarbonate anions, and a good source of that would be something like sodium bicarbonate. And again, we chose the sodium salt for the same reason, because the sodium ion cation is neutral and it renders good solubility to the compound. So here's a classic sort of way that I might prepare a buffer. So suppose I wanted 200 milliliters of a buffer, and I wanted the concentration of each of the two components in this buffer to be 0.5 moles per liter. The buffer I'm making is acetic acid in equilibrium with acetate anion. So how typically a chemist would do this is I want 200 mils total, so I want 100 mils of each of the two components. I'm going to end up diluting my components. If I mix these two together, the concentrations will be halved. So as I want a final concentration of 0.5 moles per liter each, I'm going to mix together 100 mils of 1 mole per liter solutions of each of the two components. And I'm using here sodium acetate as my source of the acetate anion. So when I mix all of these two together, what do I end up with? 200 mils of buffer solution with concentration of each of the two components 0.5 moles per liter. Okay, so why does the buffer resist changes in pH? Well, if you add any strong acid to it, what's going to happen is that the conjugate base will consume it. And if you add any base to it, what's going to happen is the weak acid will consume it. Now, because we prepared our solution with a relatively high concentration of both the acidic of both the weak acid and its conjugate base, when we add sort of small additions of strong acid or strong base, the pH is not going to change that much. So how do we know the pH of a buffer solution? Well, it turns out that we could do ice tables, but there's a little shorthand called the Henderson-Hasselbalch Equation. And the Henderson-Hasselbalch equation says that for a buffer, the pH is given by the pKa plus the log of the base concentration divided by the acid concentration. And later on we'll show that you can also just use moles in here. So pKa equals the log of the moles of base over moles of acid. Now there is a little bit of a complication here. Most of the buffer calculations that you're going to be asked to do are going to be complicated because the volume will be changing. So our concentration is going to change from where they started because we're adding liquid to the system, right? Because normally what we're trying to figure out is how the buffer responds to adding a solution of acid or base. And that's where there's a lot of value in this second form of the Henderson-Hasselbalch equation, because there's no volume term when you use it expressed in that manner. Okay, so let's have a look. We've got a buffer. We've got 100 mils of that buffer. It contains 0.5 moles per liter acetic acid and 0.4 moles per liter sodium acetate. So this is our source of the acetate anion, which is our conjugate base, and this guy here is our weak acid. And what we're asked to figure out is, how does the pH change when you add 2 mils of 1 mole per liter sodium hydroxide? So sodium hydroxide is a strong base. So we're adding a fairly small amount of strong base. And what we're hoping is that our buffer is good and the pH doesn't change a lot, right? It's going to go up a tiny bit, if anything, because we're adding some strong base. So if we want to calculate the change in pH, we have to figure out where we're beginning. So we're going to use the Henderson-Hasselbalch equation to figure out the initial pH. So initially, the pH is equal to the pKa plus log of the base concentration over the acid concentration. And when I look up in tables, I find that the pKa over acetic acid is 4.75, and then I've got to add to that log to the base 10, this is, of my base concentration, which was 0.4, over my acid concentration, which was 0.5, so it's 4.65 is where I'm beginning. Now, what I'm going to do is I'm going to figure out how many moles of each of my two components that I have in my buffer. So I've got 100 mils or 0.1 liter of my buffer, and the concentration of my acidic component was 0.5 moles per liter. So what that means is I've got 0.05 moles of my weak acid, and then I'm going to do the same calculation for my my conjugate base. And I've got, that was 0.4 moles per liter, that was given in the problem, there it is, and it's in the same 100 mils to start with, so I've got 0.04 moles of my acetate anion, which is my conjugate base. All right, so now we're going to mix everything up, right? We've got this buffer at a pH of 4.65, and now I go ahead and add my 2 mils of strong base. So this is where I'm starting, and this is what I'm going to add. So how much strong base am I adding? Well, its concentration was 1 mole per liter, and I'm adding 2 milliliters, or 2 by 10 to the minus 3 liters. So I'm going to add 0.002 moles of sodium hydroxide. So what is the effect of adding hydroxide to this buffer? Well, this sodium hydroxide is just the source of hydroxide ions. What's going to happen is my hydroxide ions are going to consume some of my acid. And by consuming some of my acid, they're going to produce some acetate, or my conjugate base. So what's going to happen is that the concentration of my weak acid will decrease, and the concentration of my conjugate base will increase. So initially, I had 0.05 moles of my acetic acid in 100 mils. and I had 0.04 moles of my acetate anion in 100 mils. And then I added 0.002 moles of hydroxide ion in 2 mils. So that's going to consume some of my acid, right? So that leaves me with 0.048 moles of my acid in a total of 102 mils. So now I look at my acetate anion. Initially I had 0.04 moles dissolved in 100 mils. By adding the base, adding the hydroxide ion, I produced 0.002 moles, but I also increased the volume by 2 mils. So after the addition, I'm going to have 0.042 moles of the acetate anion dissolved in 102 mils. So now I've got everything that I need to go ahead and use the Henderson-Hasselbalch equation to calculate what the new pH of the buffer is. So let's have a look here. To calculate the concentration, remember it's just going to be moles over liters. All right. So my pH is equal to the pKa plus log of my base concentration, my acetate anion concentration, divided by my weak acid concentration. And so I can go ahead and do that. So the pKa is 4.75 plus log of, and here we are, we're doing this, the moles of base divided by the liters of solution. All right, and because we've got 102 mils, that's just going to be 0.102 liters. And then I have to do my moles of acid divided by my liters of solution. All right, so I'm just going to pull out the volume term, and you can see that it actually cancels out. So that's why I can just use the moles if I want to, and the Henderson-Hasselbalch equation works just fine. So when I do the math on this, I end up that after the addition, the pH was 4.69, and I'm happy because it went up a little bit. Now the question asks for the change in pH, right? So what happened to the pH? We went from 4.69. We ended up at 4.69 and we started at 4.65, so it went up by 0.04. So it barely went up at all. So now it would be a good opportunity to do a buffer calculation, where this time we're going to take a buffer, and instead of adding some base to it, we're going to add a little bit of acid, and we'll see what happens. Now in this case, there should be a modest decrease in the pH. So we're going to look at a buffer, and what we're going to do is we're going to be adding 1 ml of the strong acid HCl, and the concentration of that acid is 1 mole per liter. The buffer that we'll be looking at, we've got 100 mils of it, and it's comprised of 1 mole per liter hydrofluoric acid, that's going to be our weak acid, in equilibrium with a solution that contains its conjugate base, the fluoride ion, also at 1 mole per liter. So this is the setup that we've got, and the concentration of each of our components here are 1 mole per liter. So our acidic and a basic component have a concentration of 1 mole per liter. So let's go, and then what we're going to be adding to that is some HCl. So what are we starting with? Okay, so we're going to do a couple of things here. We're going to figure out the number of moles of our acidic and basic components to begin with. So they're both 1 mole per liter, and we have 100 mils or 0.1 liters of each. So that means that we've got 0.1 mole of both our weak acid and our conjugate base. So I'm also going to go ahead and I'm going to calculate what the initial pH of our buffer is. Remember, pH is equal to pKa plus log of the concentration of our base over the concentration of our acid, or as I mentioned previous, we could have put in the number of moles. It will work out just fine. So when I do that, I get that the initial pH of the buffer is 3.17. So what's my change? Well, I'm going to be adding this strong acid, right? And I'm going to add 1 ml of it. So what I want to do is figure out how many moles of this acid that I'm adding. So the concentration of the strong acid was 1 mole per liter. The volume that I'm adding is 1 milliliter, or 1 by 10 to the minus 3 liters. So I'm adding 0.001 moles of acid. And what is the effect of adding that acid? It's going to turn some of my fluoride anion into hydrofluoric acid. So what it really means is that the concentration of HF is going to go up by 0.001, or the amount of HF will go up by 0.001 moles, and the amount of fluoride ion will go down by 0.001 moles. So I'm going to do some math here. I started with 0.1 mole of HF and 0.1 mole of fluoride ion. I added 0.001 moles of HCl, which makes the HF go up by 0.001 mole and makes the F minus go down by 0.001 mole. So here I am at the end here, and those amounts would have been dissolved in a total volume of 101 milliliters. Now, I don't have to worry about, that business of dividing through by 101 milliliters. I'm just going to put the moles directly into the Henderson-Hasselbalch. So the pH is going to be equal to the pKa plus the log of the moles of base over the moles of acid. And when I do that, what do I get? 3.16. So initially, I had a pH of 3.17. Finally, I ended up with a pH of 3.16. The pH went down by 0.01 units, which is a tiny little amount, and that makes sense because we did add acid. So having done a couple of these, you start thinking about how you might shortcut it, and what you realize is that you can kind of jump to the end and you can formulate some equations that look a little like this. So you want to calculate the pH of a buffer after the addition of a small amount of either strong acid or strong base. So recognizing that adding acid destroys base and creates your acid, then you can rewrite the Henderson-Hasselbalch equation to look like this: that if you're adding strong acid, the pH of your buffer will be, after the addition, will be equal to the pKa plus log of your initial moles of base minus the moles of acid added, divided by your initial moles of acid plus the moles of acid that you're adding. Similarly, if you're adding strong base to your buffer, the pH after the addition of the strong base will be equal to the pKa of your weak acid plus the log of your initial moles of base plus the moles of any base that you're adding, divided by your initial moles of acid minus the moles of base that you added. So you can kind of just do these in one step fairly quickly. There's a little bit of messing around in converting everything to moles, but it's not that difficult. Just keep in mind, when you're adding and subtracting in either the numerator or the denominator of a fraction, keep those things in parentheses so your order of operations occurs the way that you're expecting when you enter it into your calculator. Okay, so I think we've kind of concluded the quantitative portion of this section. Now we want to talk about some sort of important things to consider about the use and preparation of buffers. So one of the things that we're interested in is over what pH range would you expect a particular weak acid conjugate base pair to be an effective buffer? And this is known as buffer range. And then the other thing that we might ask ourselves is how much can we, strong acid or strong base, can we actually add to our system before we are beyond what the buffer can deal with? And that's referred to as buffer capacity. So I'll give you some guidelines for both of these things now. So the rule of thumb as far as a buffer's effective range is concerned is that we don't want one component to be more than 10 times the concentration of the other. That is, we want the ratio of our conjugate base to our weak acid to never be, such that we have 10 times more of one of those things than the other. So when we do some math here, let's just say, imagine that we had 10 times as much base as acid. We can calculate the pH for that scenario. It would be the pKa plus the log of 10 on 1. And the log of 10 is just 1. So this would be, a pH of pKa plus 1. Okay. Now, what about if we had the other scenario where we had 10 times more acid than the basic component? So 10 times more of the weak acid than its conjugate base. So this would be, the pH of this buffer would be equal to the pKa plus log of 1 on 10. And the log of 1 on 10 is minus 1. So we want our, the sort of the useful range for our buffer is going to be somewhere between the pKa plus 1 and the pKa minus 1. So we tend to pick a weak acid conjugate base pair that has a pKa within 1 unit of the pH that we'd like to buffer at. So there are tables of pKa's in the back of your book, and if you were looking to buffer at, say, a pH of 7.4, that's a physiological pH, you're going to look for something that has a pKa between 8.4 and 6.4, and there'd be a variety of options there for you. Okay, so what about buffer capacity? Well, what we find is that the best buffer capacity is when we have a ratio of the conjugate base to acid component that is closest to 1. So we want to have, if that's going to be the case, we want to have the pH that we want to be buffering at should be exactly equal to our pKa. So we tend to try and pick the pKa to align with the pH that we want to buffer at in order to maximize buffer capacity. The other thing that we want is we want the concentration of the acidic and basic components in our buffer to be as large as possible, and most importantly to be greater than that of any acid or base that we might add to our system. So we're going to try and pick things that are very soluble. So typically things that are very soluble include stuff like acetates, sodium salts. So we're going to keep in mind our solubility rules, okay? So that would be the other kind of parameter that we would look at. We want our weak acid and its conjugate base to be as soluble as possible so we can maintain a high concentration.